All right, I guess let's get started. All right, so hello, everybody. Welcome to the final lecture of the Battlecode lecture series. Today we're going to be talking about bytecode hacking and optimization in Java. So let's get started. Okay, so for some goals for today, we want to show you kind of what bytecodes are in Java and how exactly they work and why we actually care about them for Battlecode and how we actually consider them when you're running your bot. Also, we want to show you an introduction to bytecode optimization. So how to reduce the bytecode amount in your program and also why that is important. So let's start by talking a bit about the JVM and some bytecode basics. So essentially, when you compile your Java program, it gets compiled into a list of bytecodes, which essentially are like instructions that the JVM knows how to execute. And it will interpret these instructions and kind of run them on your actual computer. And it's kind of like an instruction set. So some of you may be familiar with assembly. It's kind of similar to that, except traditional assembly is kind of more focused on bits and numbers, and that's kind of all it can do. Whereas the bytecode instruction set is more high level, so it can work with both primitives and objects and do some high level things. So we think of a bytecode as an atomic instruction, which essentially means that you're guaranteed that the whole thing is executed. And it's not like you don't have half of it that runs or anything like that. It's fully executed whenever it runs. And because of this, it's roughly equivalent to a single assembly instruction in native code, depending on what bytecode you're running. Some of them are, again, very high level, so it would not be directly translatable, but some of them are very similar. So when you compile your Java program and you get the output.class file, they store a sequential stream of these bytecodes, and that way the JVM can interpret it in order. And the important thing about the JVM is it's a stack-based architecture, and we'll talk about what that means in a minute. So essentially, the stack-based architecture means that each method that's executed in the program operates in what's called a stack frame. And the stack frame, essentially, if we look at this diagram here, has an operand stack, and that keeps track of, it's basically just a stack of values that the instructions can push onto. And then that way, when a bytecode gets executed, it's essentially like context for the bytecode. And then we also have the local variable array. Those are places that we can store values if we need to reference them later. And we also have access to the constants pool. So any constants in the classes that we might need to reference during our program are available in the constants pool. And the way it works is, so the execution stack basically keeps track of all of the methods that are being run. That way, if we are calling methods inside of methods, we know which method we're in. And for each method in our execution stack, we create a new stack frame that is local to that method. That way, if we're in an outer method and we call an inner method, the inner method doesn't affect the stack frame of the outer method. So when we return from the method, we know exactly where our state was when we left off. So why do we care about bytecode for Battlecode? So essentially, in Battlecode, we need to guarantee that both teams have equal resources in terms of computation time. We don't want one team to be spending a very long time per turn. And so we do that by limiting computation with bytecode. So why exactly do we use bytecode to do this? Well, because it's computable. So what that means is that we can look through the program before it runs and figure out how much different parts of the code, how much bytecode different parts of the code take to execute. And more importantly, it's deterministic, which means that every time we run the program, it will always use the same amount of bytecode. This means that it doesn't matter what machine it runs on, it'll always be the same, and same for per execution will always be the same. So this is in contrast to, for example, runtime. If we wanted to say that a bot is limited to maybe 10 seconds per turn, this wouldn't be good because computers aren't perfect. Some turns might take longer, might take less time for the same exact code that's running. And also some people's computers are faster than others. And so by using bytecode, it's very fair and deterministic. And it roughly does correspond to computation power. You can imagine the more instructions that you're running, the more computation it will require to actually run the instructions. And so it's a good metric that is roughly equivalent to computation power. Important thing to note about Battlecode is we keep the bytecode limits fairly low. And that's because we have lots of bots to simulate and we don't want to spend a long time. And so, for example, an A* search can very quickly go over the bytecode limit. And so that's why it's important to focus on optimizing your algorithms and creating algorithms that aren't traditionally or are more specialized for the competition itself. Okay, so let's do a quick demo of bytecode, and we'll look into a bit of what bytecode actually looks like and how you can look into your program and see what it's doing. So we have this simple program here called vector magnitude, and essentially, let's just run it quickly. Let's see, vector magnitude. Okay, so we pass it in an X value, so we'll say 1. We pass it in a Y value, we'll say 1, and it will print out the magnitude of this vector. So if we look at the code, all this means is the square root of the X component squared plus the Y component squared. So fairly simple function, but let's actually take a look at what this looks like in the bytecode world. So when you normally compile Java programs, you do Java C to compile and you call Java to run it. But Java also ships with a program called Java P. So if you call Java P-C and then the name of your program, you can actually have it print out the bytecode of the program. So if we look at this, we can see our main function here with our arguments, and it's doing a lot of crazy stuff in here, which is fine. And we can see how it's, yeah. So let's not look at that for now. What's more important is we'll focus on this get magnitude function. Let's try to fix this. Oh no, it's gone wrong. Okay, let's do that again. Okay, so here we go. So we can see our signature here. So we have public static float get magnitude with 2 floats as parameters, X and Y. So let's take a look at this program. So first thing it's doing is it's calling float 0 2 times. So if we think about what this is doing, this instruction, the right side of it is loading the variable in that index 0 from the local variables array onto the stack. So when we call a method, its parameters are stored directly in the local variables array. So if we think about this method here as a list of integers, then index 0 will contain our X value or our floats, our X value and our Y value. So when we call float 0, it will take the parameter at index 0, which in this case is X, and it will put it onto the operand stack. So we do this 2 times because the first thing we do in our square root function is we square X. So we need to load X onto the stack twice. And then the next thing we do is we call fmul, which will take the last 2 operands on the stack and multiply them together. So this will, in this case, multiply X by itself. It will pop these 2 things from the stack and then put the result back onto the stack. So once we call this, all we'll be left with is the result of X times X, which in this case will just be, from our example, we just had 1, so it would just be 1. Then for the next part, something similar, we call fload, but with 1. And in this case, it will load the variable at index 1 onto the stack. So in this case, that is Y. So we will load Y onto the stack 2 times, call mul, which will pop those 2 values off, multiply them together, and then store the result on the stack. So by the time all these bytecodes are done, we're left with 2 variables on the stack, which will be the result of the both multiplications. So then after that, we can call fadd because it takes the last 2 operations on the stack or operands on the stack and adds them together. So once we do all that, we're left with the final result inside of here. Now we can do some type conversion, which is not super important. We call invoke static on the square root function. Finally, we do some more type conversion, and then we return the value on the stack. So yeah, so something that seems like kind of like a small function that's not doing a lot does have a lot of operations involved in it. And so it's kind of interesting to see how this gets compiled into this. Does anybody have any questions about that or anything that I've talked about so far before we move on? Yes. Okay, well, not exactly. I'll get into that in a bit. But to answer your question, no. I'll just say now. So the 12 refers to how many bytes it is, how many bytes. So from here to here is 12 bytes, but it's not necessarily 12 byte codes. So yes, but I'll get into that. Any other questions? Great. Okay. So that was a little basic quick intro to what bytecode looks like. Let's talk a little bit more about how that relates to or how it actually gets analyzed in Battlecode. So before any code gets run, engine will walk through the compile program tree and basically compute the bytecode cost of each section of your code. What's important is that these are all basic, all these code that we create or we analyze are basic blocks, which means that there's no way that it could have any different amount of bytecode for each execution. So for example, a basic block will contain no functions or branching, because that way it's a deterministic amount of bytecode for each call. And then after each block gets executed, or at the end of each block, we create a checkpoint with the block's total bytecode cost. And then while the program is actually executing, we keep track of the bytecode that's been executed so far using those computed costs. And then if at any point you exceed your bytecode budget, the execution gets halted, and you're basically your turn is done for the bot and it's skipped. And so it's important to notice about this is that you're only penalized for the total number of bytecode you use. So we only cut you off based on the number, not necessarily runtime or anything else. So it doesn't really matter what your code looks like or if it's slow, as long as it is in the bytecode limits, that is all that matters. So let's talk about a little bit more about your question earlier. So if we look at these instructions, which look familiar from what we looked at before, we can see that there are two different instructions here. We have iload 0 and iload 5. So this first one, iload 0, is a special instruction, which loads the integer from local variable 0 onto the stack, as I had mentioned. Because it's special, we don't actually need to pass it any arguments, so it is only 1 byte, 0x1a, and it will load value 0 onto the stack. However, this other one, iload 5, is 2 bytes because it needs to actually, the instruction itself is 1 byte, 0x15, followed by the argument, which is 5, 0x05. And so in order to call this bytecode, it requires 2 actual bytes of memory. But so we can see in the offsets here, it ends at 1. This one ends at 2, and that's kind of similar to what we saw over here. This demonstrates how the actual size of the instructions. But despite this, both of these bytecodes only, or at least for our cases, are only counted as 1. So this total section, so these two would be counted as 2 bytecodes, and these two would be counted as 2 bytecodes, just regardless of how many bytes they actually take up. Is that clear to everyone? Anyone have any questions about that? Great. Okay. So in a similar vein, the code complexity also doesn't matter. Just because your code looks a certain way does not necessarily mean that it's more expensive to run. So a good example of this are switch statements. Although they're functionally equivalent to if-else statements, they actually do use less bytecode, and we'll go into an example on that in a second. Sorry. Okay, so let's look at that quickly. Okay. So we have this program here called hidden number. Essentially, it will take in a user input, 1, 2, or 3. And depending on the input, it'll print out one of these member variables here. So let's run this quickly. Let's see. All right, so if we put the number 1, it should return us number 1, which is 3. So there we go. We put in 2, it'll return us 5, put in 3, return us 7, and then anything else we put in, it'll return us 0. So fairly simple, but if we look at the code here, we can see that there are 2 ways that we can achieve this. The first way is simply using if-elses. So we get the user's input and selection, and depending on the selection up here, we simply just check if the selection is equal to 1 or 2 or 3, and then return the correct appropriate value. Or we can use a switch statement down here. So let's first start by looking at the, let's look into this program and see, take a look at the first get number function first. Okay, so let's take a look at our get number function up here. So here we can see our signature, static int get number int. So first thing we do is we call iload 0, and what that does is it loads our first parameter of the function onto the stack, so that in this case that's our selection. And then we load another number onto the stack. So iconst1 will load the constant value 1 onto the stack. So now our stack has our selection and then 1, and then we compare. So we check if it's equal to 1. Well, in this case, we check if it's not equal to 1. And if it's not, we jump to the next comparison, which is here. So we compare, we jump to 9. And if we look at offset 9, this is the start of the next check. This one will load our selection on the stack. It'll load the value 2, and then it will check if these are not equal. If they're not, we go to the next check, and so on. And so there's a lot of instructions that are taking place during this function. And so we can kind of see how something so simple can still take a lot of bytecode, even though it's not really, doesn't really need to. So let's take a look at now the optimized version, which is functionally equivalent using a switch case. So here we have get number optimized with our int parameter selection. So first thing we do, we load our selection onto the stack. And then we have this table switch bytecode. And it's a pretty big looking bytecode, but again, it's only one bytecode for the sake of Battlecode. And so what this does is it will take the value on the stack, which in this case is our selection. And depending on what it is, it will jump to a certain part of the program. So if the value is 1, we will jump to offset 30, which we can see is here. 2 is 34, brings us here, and then 3 is 38, which brings us here. So let's just say our selection is 1. We'll jump to offset 30, which is here. This calls get static. Number 2, which we can see over here, will load our value of num1, and it will return it immediately. So, and this will happen for all 3 numbers. So you can see over here, it loads num2, returns, loads num3, returns for all 3. And we can see that no matter what selection you put, in worst case, it will always take 1, 2, 3, 4 bytecodes to run this function at most, no matter which selection you have. That's in contrast to the original function, which if you decided to put, if your selection was, for example, 3, you'd have to run through a bunch of these. You'd have to come through this whole list and go through each comparison in order to get down there, which costs way more bytecode than doing the switch case. Even in the best case, if your selection was 1, it would still take 1, 2, 3, 4, 5 instructions to run this function. So in every single case, the switch statement is always better. So that's an important optimization to keep in mind while you're writing your bots. Does anybody have any questions about that? Great. All right. So what are some optimization goals? So when we're optimizing our program, our goal is to reduce the total instruction count to a minimum. And we saw one way of doing it, but there are definitely many other ways that aren't, and there are definitely many ways to do it that are both kind of just refactoring like non-functional parts. And obviously there are still things that you have to do as a competitor to reduce your algorithm complexity and all this stuff. So one other thing we can look at that we can kind of just do just generally is loop optimization. So interestingly enough, the way you design your for loops can actually drastically impact how much bytecode you use. So let's take this basic loop for an example. So we have an array of integers called values, and we want to loop through all of them and set them to 0. So this loop is kind of silly because it doesn't actually do anything, but we'll just pretend it does. So this is an enhanced for loop, which I'm sure you guys are familiar with. We just loop through each value in values and set it to 0. So something that's this simple actually takes 10 bytecodes per iteration, which is a lot. But there are things that we can do to reduce that. So let's kind of talk about a little bit about why this happens. So when we are running an enhanced for loop, we have to store this value variable. We have to keep track of a loop index. We have to keep checking the array length and all this stuff. And that's part of the reason why it takes so much bytecode to run this loop. So one simple thing we can do is we can turn it into a more of a old-fashioned loop, which is just I equals 0, I less than length. We keep track of an iterator, and we pre-compute the length and store it in an integer. And by doing this, it does actually end up saving 1 bytecode because it does not have to keep checking and loading the length every single time. And so even though this code seems like it's more complex, it does actually run, or does have less runtime, or it has less bytecode. And so it's a good example of when code that seems more complex actually is better for your bot. So let's take this a bit further. I do have this written out here, so we can actually take a look at the bytecode for these loops. Okay, so let's take a loop at the first loop. So here we have loop 1. This is the first one that we saw, where we loop over each value in values and set it to 0. So there's a decent amount going on here, but if we want to check specifically how much each iteration is taking in bytecode, we can take a look at our go-to statement. So if you think about a loop, it's going back to a certain place of the code over and over again. And so whenever we see a go-to, we know it's part of our loop. So this go-to is telling us to go to offset 10. So this is our first instruction inside of the loop. So if we count these 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the loop has 10 instructions inside of it for each iteration. So for the sake of time, we won't go through all of what's going on, but it is loading the value and iterating the variable and checking the length and doing all this stuff every single time in here. So let's move on to the second one, where we pull the length out and do a traditional for loop. We can already see it's already shorter in terms of bytecode. But if we want to look at specifically how much bytecode is in each loop, we can look at the go-to statement. So here we have go to 8. First instruction, 1, 2, 3, 4, 5, 6, 7, 8, 9. So already that optimization brought us down by 1 bytecode. And yeah, but there's still more we can do to improve on this loop. One thing we can do specifically is pull the value array into the local scope. So if we look at our class, we have values, which is a member variable. But when we want to access a member variable inside of a method, we have to push the this object to the stack. So what we can do instead is create a alias variable here called local values, which is just equal to values. Since arrays in Java are references, it's the same array. And by doing this, by doing this, if we look through the code here in loop 3, let's back up a little bit. So if we look in loop 2, when we want to get the value from values, we call load 0, which when we call a method on a member on a instance of a class, the 0 index in the local variables is always the this object. So we load the this object onto the stack, and then we call get field. And you can see here it's loading the values field. But if we look in loop 3, when we pull values into the local scope, we can see that where is it? So here we call load 0 at the beginning of the function, and we store it in the local variable 1. So now, whenever we want to reference it in our loop, we only have to call load 1 instead of having to call load 0 and get field every single time. So just that alone reduces the instruction count by 1 for each loop. So we are now down to 8. So we can count these. So go to 10. So we'll go to offset 10, 1, 2, 3, 4, 5, 6, 7, 8. So already pretty good, but there's still more we can do to this function or to this loop. We can see this last one here looks very different. But if we rewrite the loop so that the condition variable, so here we're checking, so before we were checking if I is less than length, but if we rewrite it so we check against 0, Java has a special bytecode for checking a value against 0. What we can see in the code is, so if we look back at loop 3, before we do a comparison, so we have this if, and then we check integer comparison if greater than or equal to. So before we do that, we load 2 values. So we load 3 and 2, which I'm assuming in this case is I and length. And then we check if I is greater than or equal to length. But for loop 4, before we compare, so if less than, this is what this instruction means, we only have to load 1 value, which I'm assuming is I, because we can compare it. We're basically checking if I is less than 0. And so by doing that, we can reduce our instruction count by 1 more. So we'll get down to 7, and we can count this. So go to 8, 1, 2, 3, 4, 5, 6, 7. Sorry. Okay. So just from those simple things, we're already down by 3 bytecodes per loop iteration, which may not seem like a lot, but it is 30%. And consider that bytecode count is for each loop. And that doesn't even count what you're actually doing inside of the loop. So especially when you're looping a lot, it's very important that these small additions can add up. And so when you're really struggling to get that, like, stay under that bytecode limit, very small optimizations like this are important. And the saved computation can be used for actually important things, because as we saw, we can reduce bytecode without actually changing the function of what is going on. This loop is equivalent to this one, but it uses less bytecode. So moral of the story here is optimization is important, and you should always be thinking about it when you're writing your code, both for Battlecode and not Battlecode. But yes, so that is all. Anybody have any questions about that? Great, thank you.